Hi folks, Mr. Long here. I'm going to do a screencast today on integrals as signed areas. In other words, areas that are positive or negative depending on the value of y and the direction in which we're doing the integral in terms of x. Okay, so this is the shape that we're going to work with in a few different screencasts today. This shape here, which by the way we call f at x, and it's a half circle, semicircle, then it comes down at the linear section there, and then a half circle or semicircle is cut out of a rectangle, and then it's linear all the way up to x equals 10, and then it's a horizontal line, which is also linear from x equals 10 to 12. Okay, and we're going to be answering a bunch of questions about this shape, and we're going to connect back to a number of ideas. So you've done some work already, so you should know what this represents. It means, so f of x is a y value, delta x is considered, dx is considered delta x, so that's areas, right? X times y. And then from 6 to 4 means that x is changing from 6 to 4. So I need to get the area in this diagram from x equals 4, right there, to x equals 6, okay? That's the area I'm interested in calculating. I'm calling it A3 on this picture. Okay, so this says find the area of this function f at x from x equals 4 to x equals 6. Now the first thing I should notice about this is that area is below the x-axis. Therefore, it's going to be a negative. Okay, it's going to be a negative. So this A3, which goes from 4 to 6, is this area here. So the way that I'm going to do it is I'm going to treat it as a whole rectangle, like that, and then I'm going to remove this semicircle. Okay, so let's go ahead and do that. I know the answer is going to be negative. So the way that I do it is I just put a negative here, and then I do my calculation in a large set of brackets, right? So I just take the rectangle and I remove the semicircle. So r is 1. Okay, so the negative of, and 4 times 2 is 8 because it's 4 tall, right? So 4 times 2 is 8 minus pi r squared. So pi r squared over 2 is the area of a semicircle. Pi r squared is the area of a circle. So it's going to be pi times 1 squared, which is 1, divided by 2. Okay, so it's pi divided by 2. Pi times 1 squared is 1 divided by 2. And that's an exact value there. If I want to get an approximate value, I just need to go 8 minus, that's 1.57, okay, to 2 decimal places, 3.14 divided by 2, which equals the negative of 6.43, okay, which is then negative 6.43, okay, and that's what that's equal to. So therefore, the integral, or the area, from x equals 4 to x equals 6 of f at x dx is approximately negative 6.43. Okay, and what does that represent? Well, if f at x, if that graph is a rate, then that would mean the original function, big F at x, would have a change in y value of negative 6.43 from x equals 4 to x equals 6. Okay, let's look at some other ones. Now, some of these I've put here just for lessons to help you see how to do this. So how to do there's little simple tricks that you can do to reduce the amount of work that you actually have to do. This one here says we want to get the area from 6 to 10 for the graph. Okay, and so I've just cut out sections of the graph. So it's the same function as before. I've just put in the section that we have of interest. So I want to get the area between 6 and 10, between the x-axis there and the y value. So from 6 to 8, the graph is below the x-axis, so that signed area will be negative. The graph to the right of x equals 8 is positive. Let's go back because I did calculations. Well, we can do calculations for these areas. Now, the question is, right away, can you see how I can do this without doing any calculations at all? So if I look at this, that dimension is 4. That dimension is 2. That dimension is 2. That dimension is 4. Except it's -4 because it's a negative y value. So if I want to get area, what I've got here is 4 times 2 divided by 2, and that's this area here, plus -4 from that times by 2 divided by 2, which is 0, right? Same numbers, opposite sign, right? So it becomes 4 times 2 is 8, divided by 2 is 4. -4 times 2, -8 divided by 2, -4. Right, the 2's would divide out, and I've got +4 plus -4 is 0. But I can just write 0. Anytime you have this scenario, you should immediately write 0 when you recognize that areas are equal in size but opposite in sign, right? Equal in size, opposite in sign. Okay, because this is a positive area, this is a negative area of the same size. Okay, now we're going to do a little bit of work on transformations. This is a review from grade 11. So, and we've done a little bit of this in class this year. So we're going to talk about vertical scaling, horizontal shifts, and horizontal scaling. So things like, you're going to see here, the first one I'm going to ask you to do is, so here's a piece of the original graph, okay? And we want to get the area from 0 to 3 of 2 multiplied by f of x. Okay, so remember when we do this, that is a vertical scaling, or at least some people call it a stretching or a compression. So if something originally was 3 units tall, okay, if it was 3 units, something was 3 units tall, and then A ended up being 4, well, that would mean the new object would be 3 times 4, or 12 units tall. Okay, it's a vertical stretch. And that's why we say the new y values are just A multiplied by the old y values. So let's take a look at what this might look like graphically. Okay, what would this look like graphically? So I've got a graph of f of x, which is this graph here. I'll just highlight that. That's f of x, right? Then I've got this value here of 2. A equals 2. So f of x represents the y values in the original graph. The 2 represents a multiplication of those y values. So what would our new graph look like? Well, we would go up to 2, right? 1 would go up to 2. This y value of 1 would become 2. This y value of 0 can't change, okay? Because 0 times anything is still 0. And then this value here, which is at -2, would become -4. Okay, so if I'm to get the area of this, I've got a whole other shape that I have to deal with. That's not a half circle anymore. It's an ellipse. That's a little bit more complex. And then I have another different calculation there. But is there another way to handle this? Okay, is there another way to handle this? Well, I think there is. Multiplication, I can change where that multiplication occurs. I can bring the 2 outside the integral sign and go, well, that's just 2 integrals of 0 to 3 of f of x dx. So now I just have to figure out what this is and double it, okay? What that is and double it. So let's go back and do that. So to get the integral from 0 to 3, I'll get the highlighter out. I need to do this area here and that area there. Okay, so this area here is, we've already calculated something like that. It's pi r squared divided by 2. And if we notice, the radius is 1. Okay, so it's pi times 1 squared divided by 2, which is pi divided by 2, or 1.57. So it's going to be 2 multiplied by positive pi over 2, pi r squared over 2, plus and then I need to get this area right here. Well, that area is -2 tall and 1 wide, and it's a triangle, right? So base is, we can see here, 1, and the height of that triangle is -2. So the base rather is 1, the height is -2 divided by 2. Okay, so I've got then two groups of 1.57 minus 1. Okay, so that's two groups of 0.57. Two groups of 0.57. And that equals 1.14. Okay, it's a positive area of 1.14. And that, folks, would be the integral from 0 to 3, x equals 0 to x equals 3, to f at x dx. And that would be our final answer there. Okay, again, pause, rewind, go over these things as you need to, okay? All right, let's look at this one. And what we see here is, this is showing f at x minus 3. So f at x minus 3 means I'm shifting to the right by 3. Okay, so I'm taking the graph of f at x. So this is our graph of f at x. What I'm going to do over here is I'm going to make the graph of f at x minus 3 over here. So I'll take some key points there, 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 and there. And I'll shift each of them to the right by 3. Well, actually, I can't go to the right by 3 down here. So I'm going to take this point, this point, this point, this point. Because remember, x minus 3 shifts to the right because it's x minus p, right? I think I put that down here. So f at x minus p shifts to the right by p. In other words, our new x values, we just take the old x values and we add p. So even when it's minus, it shifts to the right. Okay, so f at x minus 3 means we go right by 3. So this 0 here moves to there. This location here moves to there. Oh, whoops, it's 3. Sorry, folks. Okay, sorry. 0 here will go to 3 here. X equals 1 here. We'll go to x equals 4 there. X equals 2 there. Goes 3 to the right to get 5. Okay. Oh, look at this. I can stop now. Because look at I'm asking for the area between x equals 3 and x equals 5 on this new graph. Well, there's my new graph. My new graph is this part right here. So whenever you have transformations, what you want to do is relate it back to the original. Okay, the original. So when I'm being asked to find the area between x equals 3 and x equals 5 for a graph that's shifted to the right by 3, that means the original function is 3 to the left. So what should I do? Well, that means I'm going to look at the original 0 to 2 of f at x dx. Okay, because 5 minus 3 is there. Minus 3 is there. So it's the same thing as getting the area on the original graph between 0 and 2. Well, we know what the area is on the original graph between 0 and 2. We've already calculated it before. It's 1.57. Okay, so that means that the integral from 3 to 5 of f of x minus 3 dx equals 1.57, because it's the same thing as f of x from x equals 0 to 2. Okay, again, you want to always relate it back to the original function. Okay, last one on transformations. Now we've got what are called horizontal dilatations or horizontal scaling. So remember that this makes it twice as steep. And we usually call that K. So I'll look up here. This is horizontal scaling. So in our case, we have K equal to 2. So our new x values then are we're going to take all our old x values and divide by 2. So what will that do to our x values? Well, it'll make them smaller. So the graph is going to be what we say is horizontally compressed or horizontally scaled by a factor of a half. Okay, so let's see here. What will this graph look like? So remember our formula that we've got there? Our x new equals our x old divided by k. And k in this case is 2. Okay, x new is x old over 2. So let's go ahead and do this. So all of our x values, now notice our y values are not changing because I'm still just using f, right? F represents the rule that I use to get the y value. So the y values are not changing. So I just divide my x values by 2, and then that's my ordered pair. So for example, well, actually let's start here at 0. So if I divide 0 by 2, I get 0. Now I'm going to divide that 1 by 2, I get 0.5. So now the top of it's going to move to right there, right? And then this 2 is going to divide by 2 to get 1. It's going to be there. So now it's compressed by a factor of 2, right? And then this here, this 3, where will it go? Well, I've got 3 here divided by 2 is 1.5. So it'll move over here to 1.5. And this 4 down here will also move. 4 divided by 2 is 2. So it'll be down here. Okay. So that's what our compressed version looks like. Okay, our compressed version looks like. So now what we need to do is let's look at the actual integral that we wanted to do. We wanted to do the integral for this from 1 to 2. Okay, from 1 to 2. Now this is challenging, and I wouldn't pretend that it's not. So I'm trying to get this area here from 1 to 2, right? That's the area that I'm interested in. Now that's a pretty easy one to calculate. Okay, it is. Or is there another way I could do it? Relating it to the old one. What I do, once I work through what shape it is, this area here, what would that correspond to on the original graph? Well, it corresponds to this area on the original graph. Okay, it corresponds to that area on the original graph. So it's the area from 2 to 4 corresponds to the area from 1 to 2. Okay, this is the graph of f at 2x, right? F at 2x is the compressed version, horizontally compressed version. So, but since it's compressed by a factor of 2, it's only half as wide at all parts. So if it's only half as wide, then that means that it's going to have half the area. Okay, so what I can do is, once I figure out that the 1 to 2 corresponds to 2 to 4, that means I can change these values, okay? So 1 to 2 is going to correspond to 2 to 4 of f at x, but it's only going to be 1/2 as big, right? Because it's only half as wide. So always relate things back to the original. So 1 to 2 on f of 2x corresponds to 1/2 of f at x from x equals 2 to 4. So what is this area from 2 to 4? Well, that area has a height of -4 and a width of 2, which means the area is -4 times 2. It's a triangle divided by 2, so it's -4. Okay, so that area is -4, but now I need to divide by 2. Okay, so the integral of f at 2x dx from 1 to 2 equals 1/2 of the integral from 2 to 4 f of x dx. So that equals 1/2 of -4, which is -2. Now there's something else you'll notice here. Since k was equal to 2, there's something here that I can do that's really quite easy. If this is 1 and this is 2 and this is also 2, that means you have to remember that this means it's half as wide as the original. Well, if f at 2x is half as wide, it's being compressed by a factor of 2. If I want to get these numbers, the equivalent numbers back on the original, I have to double them because the original is twice as wide as f of k of f at 2x. So that 1 then goes to 2. 1 times 2 is 2. Again, why is this 1/2? Because this graph is only 1/2 as wide as the original. Okay, so we're always, always, always relating back to the original function. Okay, last one. And this is a pretty simple one. So remember that I'm going from 4 to 0 in this case. I want to get the area that accumulates from 4 to 0. So what I'm really doing is I'm starting at 4 and I'm working backwards to 0. So what does that tell me about delta x? Well, delta x is going to be negative. Now the easiest way to do this is we're going to reverse our areas. Okay, reverse our areas. So we know that this right here, that area equals A1, I'll call it, equals 1.57. Now going from left to right, it's a positive area, right? And then the area from 2 to 4 is a negative area, 2 wide, 4 tall, but -4. So 2 times -4 is -8, divided by 2 is -4. A2 is -4. And now the thing is that I know that I'm going backwards, right? So what's the relationship then? It's the same thing as 0 to 4, but negative. And by the way, all of your rules like this are over here. Do you see that rule? So from A to B is the same thing as negative of B to A. Okay, if I reverse those limits of integration, instead of going left to right, I'm going right to left, and my answers, anything that was positive is going to be negative, anything that's negative is going to be positive. Okay, so what is that going to work out to then? And I always want to write my integrals, by the way. I always want to write my integrals with a lower number in the bottom than in the top. And the way that I do that is I make this negative outside. Okay, so it's A1 and A2. So what I need to do is I need to get the negative of, as long as A1 is written left to right and A2 is written left to right, it's going to be the negative of A1 plus A2, which is going to be the negative of positive 1.57 plus -4. That's A2. And what does that work out to? Well, it's going to work out to, if I expand the negative through, I'm going to end up with 4 minus 1.57, which is going to be 2.43. Okay, 2.43, positive 2.43. And that's, again, the change in y value on the original, or the area under the curve of the rate. Okay, folks, so I think that pretty much takes care of everything on this page. Make sure you're referring to the side here where I've got 8 different rules that we're working with. And I know that was a long one. What you should do now is go ahead and finish these pages on your screen on the GM board that you can do on